So for those of you who've never been here before, or maybe even some of you who have, this is the Harvard Ed Portal. The purpose of this space is to connect the Allston Brighton and broader community to Harvard University by bringing folks together for a variety of programs, this being one of them. We do offer free programs for folks of all ages, including educational, cultural, professional development. We have some workforce and economic development programs here as well. And if you are interested in any of that, check out the front desk. We have some flyers there. Go to our website. Just type in Harvard Ed Portal and you will get to our website quite easily. While you're here, we have a new exhibit in our Crossings Gallery by Maria Cuneo. It's called Rethreaded, and it's all reused fabrics. It's all a sustainability exhibit. It's very cool. And we have a mural outside that is just about to wrap up at the end of this month by Non-Issue Studio. It's called Give and Take. It's a very interesting kind of a la free library. You can go and take stuff out of it or put stuff into that boxes. So you should check it out. With our community lecture series, we bring academic experts from across the university to engage and share their research on topics as broad as canine brains, which some of you I think were at, the future of work and AI, that was in the fall, and then tonight's lecture on robotics. So tonight we're going to hear from Conor Walsh, who is a faculty member and researcher and professor at the Harvard Paulson School of Engineering and Applied Science, and you will hear more about him in a second. But before that, I'm pleased to introduce Carolyn Kirk, who's going to provide an introduction to tonight's lecture. She also serves as the CEO of Massachusetts Technology Collaborative, otherwise known as MassTech. She's been there since 2019, advocating for the state's tech and innovation sector. For those of you who don't know this, MassTech is a public agency supporting all of the state's technology sector, including robotics. It spearheads investments in the state across several tech industries, including robotics, advanced manufacturing, quantum computing, and builds collaborative and strategic partnerships with groups, including places like Harvard University. And prior to her role at the state, Carolyn was the mayor of the city of Gloucester. So that's a fun fact for you. So Carolyn, it's wonderful to have you. Thank you for joining us. And I'm going to ask you to come kick off this lecture.
Great. Thank you. I appreciate the invitation to speak here today. It's been a while since I've been in Allston Brighton. I spent a lot of time here. I'm a proud graduate of Boston College. Does anybody remember the El Phoenix Room? That was like way back in the day, the most unbelievably delicious Mexican food restaurant, although it was really a dive bar that I spent some time at. So I'm happy to be back in the old stomping grounds of Allston Brighton, and I've lived in both communities. So a little bit more about MassTech. We are a quasi-public agency, and what that really means is we are an instrumentality of the state. My board is appointed by the governor. The Secretary of Economic Development is the chair of the board. So everything that we do is aligned with the priorities of the administration, and we just have some flexibility to be able to run a variety of programs as a quasi that not the executive branch sometimes doesn't have the flexibility to do. So across that spectrum, you mentioned some of our tech areas, and really what we're able to do is bring in the talent to be able to work with our academic partners, our industry partners, and our other partners in government. So I'm sort of the orchestra leader of the guy who's running the quantum program and the gal who's running the AI hub for Massachusetts, and our folks with manufacturing background and cybersecurity and the other tech areas. And so in a lot of, besides grant programs, what we also do is we have convening power. So we convene a lot of those aspects of a particular ecosystem. And that allows us to have sort of a front row seat to what is around the corner and maybe where do public dollars have the most impact. We don't compete with private equity or venture capital, or if there are funding streams going into certain areas. That's not our role, but there is a role for public dollars in some of the tech areas just to kind of get things jump started. And that's what we look for, is what is coming around the bend. So in robotics, we have supported Harvard. We did place an investment into in one of our funds, $3 million to build out infrastructure in human performance. And I think Conor is going to talk a little bit about that. The other piece is you can't really talk about robotics without talking about AI and manufacturing. And so we have a pretty robust program around AI. And so one of the examples, we're running a challenge. AI is a voracious consumer of data. And for the models to really work and solve big problems, you have to have data. So we're running what we call an AI models challenge. And one of the awards that we gave was to WPI. And the team there, they're looking at the waste stream. And if you go to an incinerator or a recycling facility before anything gets incinerated and they're sorting and processing, that waste is coming across a conveyor belt, and things are being hand picked, right? And it's if you have single stream recycling, you have a lot of different materials in there. So the team at WPI is using computer aided vision in order to observe what it is that's coming through. Is it plastic? Is it paper? Is it metal? Is it rubber? Whatever that material happens to be able to build an algorithm that says, okay, now I can use my conveyor belt to better sort, because now I know what I'm seeing. And then the humans in the loop are able to add a higher value rather than just picking and tossing. So it's a pretty interesting example that is underway right now, but that data doesn't exist. So that's the kind of thing that big problem is waste, right? And how we deploying robotics and AI to tackle that. Those are just a couple of examples. 2 years ago, I think Governor Healy passed a bill. It was called the Mass Leads Act, which is a big economic development bill. And we are responsible for implementing the robotics aspect of that bill. And we've stood up 2 programs in robotics. One is what we call a digital twin. So a digital twin is if you are a company or a researcher and you want to use a robotic device for something, rather than like invest in the robot itself and have that be built, you can build a twin of it on the computer, and you can look at where the defects are in that robot. You can make your corrections, you can do modeling, you can do a lot of different things before you actually have to build out that robot. So the digital twin initiative has been way oversubscribed. There's a lot of companies that can advance their technologies if they didn't have those startup hard costs of the actual physical building for prototyping purposes. So that's one example. Another example that we're standing up is what we're calling Robo Bench. And this is an opportunity for researchers or startups or companies that are trying to transition into maybe just one production line to be roboticized or automated, is to be able to access the tools in a community space that you don't have to invest in, so you can test your concept and your ideas. So again, it's public dollars that are accessible to the public good, in the sense of allowing access further for the types of innovations. We work with a lot of manufacturers. There's 6,000 manufacturers in Massachusetts. And, the big manufacturers, Johnson and Johnson, they are fully automated. They've got, very sophisticated AI. They have sophisticated robotics on their manufacturing floor, and they have uh, you know, just fully integrated. But if you're a manufacturer in Western Mass building, one or two things, and you want to automate that, you need data, you need some investment, you need guidance, you need tools, you need, support. And so part of what we also do is to, for example, make a digital twin available or allow access to some community space like a robo bench in order to help that manufacturer to modernize their program and their process. And, these manufacturers really feel the heat, right? That they need to, keep up and remain competitive. And so we're doing everything we can to help with that. Another one of our divisions is the Mass eHealth Institute, which is, I have to say, I was talking to Professor Walsh. It's probably one of my favorite divisions at Mass Tech because they're working on the digital health, the wearables, and the ability for the combination of your data scientist, your mechanical engineer, your electrical engineer to miniaturize and create a wearable that could literally save your life is pretty profound. And so, and we want all of that manufactured here with the latest and greatest technologies. So that just gives you a little bit of an idea of what we are focused on in the Commonwealth. And that's just a small slice. The portfolio is pretty big. So masstech.org, you can learn a lot more about us there. I am pleased to introduce the speaker of the evening, Conor Walsh. He's the Paul A. Maeder Professor of Engineering and Applied Sciences at the John A. Paulson Harvard School of Engineering and Applied Sciences. We've had the opportunity to work with Professor Walsh and his colleagues most recently during that development of the proposal and so, like, I hate government acronyms, so hold on. The New England Robotics Accelerators Training and Entrepreneurship, or Generate program. And I think I missed a few of the words. Okay, so you can explain it. Professor Walsh is a strategic innovator and a visionary in the field. He is working through innovations around wearable robotics and technologies. Usually I have my Aura Ring, I have my eGym that I use at the Y for my AI generated strength training workout, and I have my Apple Watch. So I love the work that you're doing. I'm a walking data center and I'm a big believer, big believer in it. But it really is helping with quality of life. And in not too long ago, folks who didn't have the benefit of some of these wearable technologies, really, they're saving lives. So my hat's off to the work that you're doing on human performance and for advancing robotics in our Commonwealth. So please welcome Professor Walsh.
Yeah, thanks a lot, Caroline, for the really nice intro. And we definitely have appreciated working with the Mass Tech team and the support from the Mass Tech team. And I'll mention that a little bit at the end of my talk today. So nice to meet everyone. Thanks for the invitation to be here. And also kind of nice to kind of be here in Allston, kind of like speaking about our research. And we've been in the new engineering building, which is just kind of down the street since 2020. So, just about 5 or 6 years or so. And I've kind of like really enjoyed kind of like being in this kind of community, and kind of happy today afterwards to kind of get to know and chat to people in the community as well. So I'm going to kind of give an overview of kind of like a lot of the work that we've been doing in our research group. If there's 3 things that I want you to kind of take away from today, and I was thinking about this kind of just ahead of time in this talk, it's kind of like, one, what are the types of teams that are required? Because this is not just me doing this work. We have teams of people doing this work. So what are the teams of people that are required in order to kind of like execute and kind of like move this kind of research forward? I think the other thing is kind of, what are the kind of like steps you take, kind of what are the first steps you want to take to kind of explore and understand and de-risk some of these approaches? And then kind of like how it really does take a sustained effort over many years to have these go from the initial idea phase to the stage that they end up kind of like really helping and kind of benefiting people in the world. So I'll talk about a bunch of projects, hopefully not too many, that will kind of give an overview, but those 3 themes will really kind of like resonate kind of like throughout the talk. So a little bit about me just before I kind of get started. So I'm originally from Dublin in Ireland. So this is us drinking some Guinness in Dublin. And we have two kids who are now 5 and almost 7. And they're my parents kind of up in the top corner. We grew up in the Dublin Mountains in Ireland. And we like to build robots at home. So this is a picture of Johnny 5. And this is trying to get our kids excited about robotics from a very early stage. Um, but I'm sure everyone here has seen Iron Man, or at least kind of heard about the movie. And so when you think about this kind of like as a concept, it's really exciting. And you see kind of people wearing these robots, having like, superhuman strength and being able to kind of do things, whether it's kind of lifting something or taking something out of the way that, a human wouldn't normally be able to do. But the big challenge and the problem is that like this is relying on kind of like this fictional arc reactor, which is this power source in the chest. And so for creating real world exoskeletons, kind of like power ultimately is one of those limiting factors in giving people true superhuman strength. That's why we don't have an Iron Man suit, yet. And so in our research group, we've been thinking about alternative approaches, and that's really been inspired by my own experience. So here you can kind of see a video of me walking. It's a little bit choppy, but when I was a graduate student kind of at MIT in the media lab with Professor Hugh Herr, I don't look so happy in this video. Look, but here we were trying to build an exoskeleton. It was part of an early DARPA program 20 years ago that would kind of take the weight from that backpack and transfer it down to the ground so that the person wearing it didn't have to feel the weight of that backpack. And so we did transfer kind of like 85% of the load to the ground. We measured that, so that was good, but it actually made it harder to walk. So instead of an exoskeleton, we created an exercise machine. That would allow you to kind of like, get a workout while you're wearing this device. But we learned a lot from that. And you can see that I'm walking differently when wearing that robot. And there's added mass kind of associated kind of with that device. So that really was at the start of the field of exoskeleton development. And we've really seen tremendous kind of explosion of this over the last decade in particular. So now there's commercial products out there that are rigid exoskeletons for people who have a spinal cord injury, being able to help them walk. And there's more and more commercial devices that you can just buy on Amazon now and kind of like use that are $1,000 or $2,000. It's really been amazing to see that move along. And there's devices for kind of that have been used for the military to help reduce risk of injury and help people walk more efficiently. So that same goal that I was working on as a student. And then we're seeing kind of exoskeletons excitingly move into the industrial and occupational settings. So really kind of taking the strain off people performing kind of very hard or strenuous tasks. And even, people have developed wearable robots for skiing and kind of other applications in the consumer world as well. So this field has like really moved forward. But when we started our lab, we really thought about the idea of like, can we create an exoskeleton, that is soft and maybe call it an exosuit? And so the idea was, can we create devices that people could wear all day that could allow people who have some mobility, but just not enough, be able to be more independent than they otherwise would be able to. Maybe they can even go under clothes. We're still working on this, but we think that in the future, some of these devices might actually be worn under clothes. And you might need to not target the whole arm or the whole leg, but how can you target just part of the body, specifically where that person needs help? And then in addition, if a person, say, has a stroke and they are, wanting to practice movement, could this device help people move better, but maybe they could kind of get better by using the device so they don't need the device anymore in the future as well. So that's really kind of driven our group. And here you can see kind of just a time lapse of our old lab. It looks similar, to our new lab in concept. So we kind of created a lab called the Harvard Biodesign Lab that brings together apparel designers, engineers and roboticists, and also movement scientists and physical therapists that all work together kind of under the one roof to kind of really develop these devices and test these devices. And so we do a lot of iteration. So it's hard to model some of this on a computer and simulate how people will react. So we build prototypes and then we kind of freeze those prototypes and then we run tests with those prototypes to try and understand how they interact with the person and how they might help with a person's movement or mobility. So I'm including these two videos here because it's really where we started. I thought it'd be interesting to kind of think about like, where did we start when we started working on some of these areas? These don't look particularly fancy. They look kind of quite crude. So here you can kind of see that, this is a soft robotic glove, that's supposed to help a person with grasp strength. And this is a very early version of our exosuit that is intended to help a person's calf muscles, so they don't have to do as much work as a person would be walking. So these are really kind of the first proof of concept. Can we create soft materials that can apply forces, integrate those into a textile-based wearable? So we're not using a rigid skeleton here. So we're not calling it an exoskeleton. And we showed that it was exciting that, with both of these, we felt there was enough merit in what we're able to show with these early demonstrations to kind of continue to kind of work in this area. So I think we can pause the videos, but I think you can see here the general concept is how do we apply forces in parallel with the underlying muscles so that the underlying biological muscle has to do less work, and the biological muscle can do less work, and the exosuit is doing kind of more of that work for the person. And so it's quite simple in theory. And the cool thing here is we can have the cable go slack. So the person doesn't have to have any force be applied when they don't want force to be applied. The system can just get out of the way. Because you want to get help when you need help, but you want the system to not be there when you don't need it. That's kind of like a key feature for these kind of like wearable robots. So again, like just showing kind of, this is kind of where we started. So like when we're in our engineering group, when we're trying to create our first prototype, we kind of get like, a bunch of electronics, a bunch of motors, we build a backpack frame, we kind of like, stick them to it as quickly as possible. We build a first textile interface. We kind of connect those cables to that interface, and we try and kind of do some quick experiments to learn. So it's a lot of this is human in the loop development where we're putting these devices on people, collecting data, and that data is kind of helping to inform the ongoing development that we do. And so this was a DARPA program that we had previously. You can see kind of like it takes many years and like many iterations to kind of like work through and kind of like make these devices better. And then it was exciting that we had a project that we were able to kind of move far enough along and build prototypes that we could show that we could help people both walk and run with less energy using kind of one of these soft wearable robots. And so that was kind of like a high impact publication for our research group, but also kind of like a cool demonstration of the capability of the technology that really showed that it could kind of adapt to different tasks and help people in different ways, not just in a lab, but also kind of like in a real world setting. And so the way that we evaluate these devices is kind of shown here in this video. So we have a motion capture lab, and we have people wear this mask. This is measuring the amount of oxygen that a person would be consuming or carbon dioxide that they're generating. And so as they're moving on this treadmill, we kind of test them without the device and then with the device. And then by comparing those two different conditions, we can understand and quantify how much is the device actually kind of helping the person. And then for this project, the cool thing was we really wanted to show that these devices could be worn kind of outside as well. And this was our first really venture in terms of getting exos outside the lab. And so apart from testing at the Army, we also kind of just did some testing in the fells, where we would bring these devices and have people kind of be able to walk and run and evaluate kind of the impact of people kind of in a less structured or kind of like in a real world kind of environment as well. And so the first project, that's kind of like the kind of work I presented so far, really allowed us to build up this kind of core expertise. How do you attach to people with textiles and soft materials, develop actuation systems that can apply forces, and have sensors on these devices that then kind of can tell the motors when to pull on those cables so you apply the right force at the right time to help people move in an efficient way. And so after we had that capability, we started to think about like, what are all the places you can use this? What are the applications where this could actually be beneficial and help people with movement? And so a first project that I'll talk about is a collaboration with Terry Ellis and Lou Awad, who are faculty members at Boston University Sargent College, so in the rehabilitation sciences. And here we were really kind of like trying to think about, when someone suffers a stroke, oftentimes they can move, but they just can't move very well. And a lot of times their walking is slow, asymmetric, inefficient, and they don't really kind of engage in their community, and they, basically don't get outside that much oftentimes. And that leads to these negative downward health spirals because they're not as active as they would ideally like to be. And so, we thought that with our exosuit, there was two specific things that we could help with. The first was that helping people with propulsion. So, when you've kind of suffered a stroke, you often can't push off to push yourself forward. And the other is kind of drop foot. So kind of your toes might drag and you might be at risk of tripping as well. And so existing orthotics, which are basically plastic braces, which haven't changed in over 100 years, they work pretty well at kind of keeping the toe up, but they also add restrictions to a person that lead to kind of people having to kind of adapt their walking to a non-natural way. And this non-natural walking basically has, consequences in terms of kind of other types of injuries, inefficient walking, that a person is kind of left, to deal with. So we thought like we should be able to solve this problem with our soft exosuit. And so here you can kind of see a prototype. So we can make a unilateral device that basically kind of like, targets just the impaired leg. Oftentimes a stroke survivor would have kind of like an impaired leg and a less impaired leg, so paretic and non-paretic. And then we're attaching kind of just to the calf and then just to the foot. And then using one of these cables, we can kind of have it pull to help with that propulsion force, to help kind of the soleus and gastroc, which are your calf muscles, push off. And then that cable with the blue arrows can get out of the way. So it doesn't actually add any restriction. And then we can turn on the other cable and basically pull up the toes to kind of help a person to kind of be able to walk in a more natural way. So you can kind of think about it as this marionette type of kind of device where it's kind of gradually releasing and pulling to kind of help coordinate a person's kind of like natural movement and walking. And you can kind of see that kind of here in this video. And then the sensors that we have are these orange sensors that are on the foot. So by putting a single sensor on both feet, we can really understand where a person is in that walking cycle and how are they moving. And then that lets us know like when to pull on those motors to help the person with their specific walking and gait. And so this is a picture of that prototype that you can kind of see here. And then near leg is the more impaired leg of this participant in our study. And then the next part of the video shows when the device is active, it really does kind of help them kind of like improve their movement, in a way that isn't maybe perfect, but it's certainly kind of better than they would have had kind of like without wearing the device. And so, we worked, we did a lot of kind of like first kind of like early studies kind of like in the lab on a treadmill. And then we wanted to figure out like, how do we create kind of like a portable system that could be used both in our lab studies, but would also be suitable for use in a clinic or in a rehabilitation setting as well. So you can kind of see here a prototype that we made that allows a therapist to still kind of guard the person safely so it doesn't interfere with how a therapist would support a patient as they're walking. And also kind of the patient or participant would be able to kind of still perform their other activities in a rehab setting while wearing the device, and it wouldn't really kind of get in the way. So a big part of, what you'll hear is like we want to build devices to help people, but also not get in the way, the rest of the time. So these are just two side-by-side videos. I'll just kind of like let them play. And you can see in the red, the suit is powered and working. And so you can see that this is allowing this person to be able to walk faster than they would kind of when not wearing the device. I won't get into all the details, but there's papers on our website if you want to kind of get into some of the data and the plots in more detail. But basically, we've shown with these devices, we can help people walk more efficiently. We can help people walk with better quality, so they're walking better, more naturally. We can have them walk faster, and we can also have them walk further, kind of like wearing these devices. So it was really kind of all of that research that really led to a partnership, with a company. So the next slide, I think, should show that. So we partnered with Rewalk Robotics, that is now called LifeWord. They're kind of based here in Massachusetts, in Marlborough. And so they licensed the technology from Harvard. And so we had filed some kind of patents, and Rewalk licensed those technologies. And then we kind of collaborated over a number of years to transfer our knowledge to them. And then they were able to kind of take the technology and turn it into a product. And it's being used in the US and in Europe as a gait retraining tool for people kind of who've suffered a stroke, which has been kind of really exciting for our team to not only kind of do the basic research, but actually see it kind of like go out and kind of like leave the lab. Where we want to go next with this project, though, is kind of thinking about how do we have devices help people in the real world. And so I won't get into too much detail on that today, but this is kind of showing the progression of our work. Devices that are more for an in-clinic use has kind of been the initial focus. We had one study where we kind of built a version of the device that we could send home, and we had 4 stroke survivors use it for their own for a month, basically, kind of like practicing kind of walking with the device. And we're working on a device now that would essentially be a powered brace. So a device that a person would be able to put on quickly and easily like an existing brace. And that would be able to kind of help their mobility, whether they're going grocery shopping or getting out in the real world, or doing kind of other tasks that they may kind of struggle to kind of be able to do. So that's kind of like future direction for kind of where we hope this project will go in the future. But I'll shift gears and speak a little bit to kind of some work that we've been doing in another area, which is focused on Parkinson's. So Terry Ellis at BU also kind of is a clinical expert in Parkinson's disease and kind of gait mobility challenges for this population. And so here, kind of one of the challenges that is kind of maybe most pressing and doesn't really have good solutions is people with Parkinson's often freeze. So they can be moving along naturally, and then all of a sudden they kind of like start to shuffle, and then they kind of like freeze kind of in place, and they're not able to move. And this really kind of is a terrible thing because people can't trust their body when they kind of try and go outside because they're worried they're going to freeze in an unexpected way. This kind of happens kind of randomly at times, or the things that are trigger it, but it's hard to predict when it's going to happen. And so we wanted to try and think about, could we use some of our technology to kind of basically help and alleviate this problem? So we created a hip version of our exosuit. I'm going to show lots of versions of exosuits. This is a hip version of it. So basically every time a person is walking, you can see that these red arrows kind of like underneath the big red curve it's basically kind of pulling as your leg is just about to come off the ground to help swing your leg forward. So we basically hypothesize that if we can kind of just inject a little bit of energy at that period of the walking cycle, we could really kind of help people kind of like with this specific condition. And so we've created various different versions of our device. Here you can kind of see kind of like this is inside the engineering building that's just down the street. But the device basically kind of functions similarly to kind of past devices. Every time a person is taking a step, a person is monitoring their movement. And then we have these actuators that are integrated into it. So motors pulling on these cables or ribbons that then applies a force to kind of help a person swing their leg kind of like as they're walking and as they're moving forward. And so we had a really exciting breakthrough a couple of years ago. We had a paper come out. And on this side, you can see this individual freezing. And kind of they're wearing the suit, but the suit is not doing anything. And then on the right side, I guess, on the right side, as we're looking at it, this person is now kind of walking kind of like without freezing. And for this kind of specific person, we tested like in the lab, outside the lab, kind of in various different conditions with their medication, without their medication. And we completely eliminated freezing for this person kind of like altogether. So this person basically doesn't have a solution. They have a hard time kind of with mobility, actually creatively uses a scooter to kind of get around because it's able to use a scooter and doesn't freeze when using that, a kick scooter, but kind of has a hard time kind of like walking. And this is just an example of the type of research we do. We're lucky that we are able to have participants come in kind of like from the greater kind of Boston community that would, have a challenge, but they kind of work with our team and help us understand kind of like what their needs and issues are. And then like, really our partners, with our team, and here in blue, that was Teresa, who's a research physical therapist from Boston University, who would be, working closely with our team as well. And so this is maybe, I'm not going to show too much data today, but like here you can kind of see in gray, this is the amount of times that this person is freezing. So you can see when their medication is on, when they're on medication or just after taking it, they freeze less, but they still freeze. But then in red is basically showing in both conditions, we completely eliminated freezing kind of for this person. And they're able to then in red and gray on the other side is gray is kind of the suit kind of off, red is the suit on, and you're able to see that they're able to walk further and be more active because of that. And this video here is showing kind of like another setup in our lab where we have kind of Doug, who's happy for me to mention his name, kind of has this kind of challenge in his home when he's going through a narrow space in his kitchen. He basically kind of that triggers his freezing and causes him to freeze. And you can see that he has a really hard time kind of navigating and kind of being able to kind of like make it through that tight space that we would all kind of do easily and take for granted. So the next video that we show will basically kind of show kind of the suit being active. So you can kind of hear it working now. And then he's able to kind of walk through this kind of like, without freezing whatsoever. And you'll kind of see his reaction kind of like at the end. So Doug is, gently encouraging us to say, when can I get one of these? He's asking us kind of all the time, sends us an email, every so often saying like, is it ready yet? Is it ready yet? Has even offered to support our research. There's so many people who kind of come to our studies and like actually want these devices and they need them now. So that really kind of motivates us as a team. But we have started doing some piloting with Doug. And so this is kind of like just his street, where he would go walking. And so, he's kind of creatively developed this device that allows him to concentrate on taking every step so that he doesn't freeze. And so you can see that he deliberately steps over this. And then by forcing himself to do that, it basically encourages his brain to focus on rhythm and then him to not to freeze. But you can see how much attention he has to put into that. And he's not able to look around or think about what he's going to do later in the day. He really just can only focus on his walking. And I think the next part of the video, you'll see the difference in terms of him being able to kind of like walk, kind of wearing our suit. And the key thing with this population is they oftentimes have the capacity to be able to walk. It's just the rhythm, that they have due to lack of dopamine in their brain is disturbed. And so they're not really able to kind of like exploit that capacity and be able to move as they would like to do. So you can kind of see Doug here. He got very excited. You can see Teresa starting to get nervous. She's like, what's he going to do next? But he was so excited, it's a little bit hard to hear, but he's basically saying, this is the first time I've walked down my street in 2 years. And, he's kind of just really, really kind of, kind of like enjoying kind of this walking experience. So, this work is also funded in part by Michael J. Fox Foundation grant. And so he wrote a letter to Michael J. Fox. He's like, when can I kind of get one of your suits that you're kind of developing? And so we actually are trying to build a version of the suit that we can give to Doug. And I think this is kind of where like we learn a lot from our participants. We kind of hear their enthusiasm. And so we're going to build a version of the suit we can give to Doug, have him use at home. And that also opens up new research questions because now we can actually study, when a person has this at home and not just in the lab, how do people use it? How does it help their mobility? And, what do they like about it? What don't they like about it? And I'd say in this world of like wearable tech, it's kind of bridging this gap between it's probably too early for industry to take on, but academia usually just does the in the lab study. So we want to be able to build devices that we can deploy in the real world, study those in the real world, learn from that, and then hopefully that can kind of allow us to optimize the technology enough where we de-risk it enough for then industry to be able to kind of take that on in the future. So it's exciting to think about kind of how we help people move more outside their homes. But for this population, it's also a challenge in their home. So these two videos here just show a person kind of like freezing as they're kind of just trying to navigate a doorway. That's one of the triggers for people with Parkinson's. Oftentimes going through narrow spaces kind of triggers freezing. And so you can kind of see here that they're kind of like really kind of struggling to kind of like move around their house. And then the video on the right, you can kind of see now the suit's being active. They can kind of like really just navigate those spaces and kind of really kind of prevents the freezing from happening, at all. And so what takes someone like 2 minutes now takes them about 30 seconds, to kind of go through those spaces. I'll shift gears a little bit and a few more times, so kind of bear with me. But on the medical side, that's probably kind of been one of the bigger focuses that we've had in our lab. But we also then got excited after we completed the DARPA program to think about what might be non-medical applications of this technology. And honestly, this was driven by kind of people on the team who worked on the technology for that DARPA program and were excited about a startup and trying to spin out a company from the work that we were doing. And so for this project, the goal was really trying to think about like, how do we kind of help prevent back pain and back injuries? Because it's a really big problem. Like the team had kind of gone out, kind of done some research, talked to people in industry, and it just came back as a really big problem. And like it was fascinating for me, but the reason is that like our body is really not optimized for carrying heavy things, and we have kind of like muscles that are very close to our spine. So there's a very small distance between the muscle and the spine. And so in order to kind of like react to the kind of moment from a box that you might be holding out in front of you, the force on those muscles has to be really, really high, 4,000 newtons, like so really, really high loads on the tissue. And it's like doing that repetitively over time really, really kind of is what causes injury. So the vision was, can we create a version of our device that would support the back for people who are performing kind of lifting and lowering tasks, basically kind of all day, every day as part of their job. And so this is kind of really common in like grocery distribution. We get packages delivered to our homes all the time, but someone is kind of packing those boxes, moving those boxes. And it's amazing. A lot of this is now being automated by robotics, but it's amazing how much of it is still actually kind of like manually performed. And people may be lifting 1,000 boxes a day. Average weight could be 30 pounds. That's 30,000 pounds a day that kind of people are lifting and kind of putting on their backs. And so again, I thought I'd for this talk today just show like where we started on this project. So these are kind of, this is Ignacio who was leading the project, but this is kind of like, the first really, really crude prototype. So, we don't instantly end up at the perfect end results. That's not really kind of how work works in our lab. We have some initial ideas of, we think we could modify this device. And if we attached it to the shoulders and the thighs, and then we had a strap that kind of like connected them, then we think that would be the right type of form factor. So this version has no motors. It's just kind of like an elastic band, and Ignacio is just wearing it and kind of like walking around. And then we start thinking about like, well, what if we actually want to program the amount of force in that cable? So you can kind of see this kind of like middle video and kind of end video. And so we start kind of adding in the technology as we start to understand a little bit more about the problem and how we might kind of connect all those kind of different parts and pieces kind of together. And so, for here, a lot of it is kind of thinking about what's the sensors that we should integrate into the device so we can detect if a person is lifting or lowering or doing something else, and then have the device kind of do the right thing at the right time so it doesn't feel like it gets in the way. And then the other thing that we try and do, which I think we can still do this more, but as a lab, we really do try and do this, is kind of get out of the lab. And we try and go and talk to people kind of like in the use cases that we're trying to target. So Ignacio went to a bunch of kind of grocery distribution centers, brought early prototypes, kind of like put those prototypes on, and tried to demo them to the kind of workers and the staff there. And that was really, really helpful to kind of guide the design and understand exactly how we should be kind of putting all the components together. So the way it works is that, there's this red ribbon that you can kind of see here. There's a motor, kind of like single motor, like a drone motor in the kind of backpack. And then basically a pulley system. So every time a person is going to bend, that motor is spinning and pulling on that ribbon to generate some force in that ribbon. And so that this ribbon is taking most of that force so that the muscles inside the body are not kind of like reacting and kind of taking most of that force. So as you can see this person move, the blue is the angle, so how much they're bending. You can kind of see down the bottom kind of like this red force profile. So if a person moves slow, the force profile is generated slowly. If they move very quickly, it's generated quickly. If they kind of don't do a full lift cycle, it kind of automatically understands that and then kind of applies an appropriate force based on how a person is moving. And so before we go to the real world to kind of test these devices, I want to just bring us back to the lab. So this again is our motion capture lab. Here you can kind of see a video of the types of setups that we would have for kind of testing these devices. So we would try and simulate what a person is doing in the real world. And here you can kind of see Jim Wan, former PhD student in the lab, and basically kind of performing an experiment where we would kind of bring in participants. We would ask them for an hour to just do this monotonous task of moving boxes kind of back and forth from one side of the room to the other. And then we would have another team member move the cart over to the other side. So they would just kind of keep going on repeat. And for this activity, but what we're doing here is we're putting sensors on the person's back and we're trying to understand what are their muscles doing while they're doing this task. And so we do that when the device is on, and when we do that when the device is not on, and then we can actually kind of quantify and understand like how much was the device helping. And so with this device in particular, we showed that it basically kind of makes picking up a 10 kilogram box feel like you're picking up a 6 kilogram box. So it takes about 40% of the strain off a person's back when they're using kind of this technology and this device. And so this also kind of is a project that spun out of our group as a startup company called Verve Motion. And so you can kind of see here kind of just a video that kind of shows kind of like what the device would look like as a product. So Verve would install lockers kind of like in a company's location. They would have an exosuit per worker who's kind of like, there. You would be able to kind of very quickly grab it, kind of like put it on in about 30 seconds and be able to kind of, start lifting and kind of go about doing your job, as you kind of like normally would. So it's been exciting to kind of see that go from kind of those initial crude prototypes that we had to kind of like now prototypes that are actually being worn by workers and kind of helping people, with physically strenuous jobs. And this is just kind of like a video that kind of shows that. So this is kind of like a person kind of like wearing the device basically in their kind of like job setting. And we think it's super cool that this person is wearing a robot, but they don't move like they're wearing a robot. You really could think that this person is just wearing a hydration pack or kind of like, some other type of backpack. So they're kind of moving in a very natural way. And the device is helping them every time they're kind of like straining their back or kind of like, exerting their back muscles. But they're not kind of adapting to the device. The device is really kind of like adapting to them. And I think that's kind of like been a really nice case study of like how we can kind of go from early stage research to kind of research that helps people in the real world. I'll just briefly show this just because I think it's exciting to me, at least. I think this is a video that kind of just shows like helping the shoulder. So this is actually kind of a project that we had through Harvard that was sponsored by JLR and Tata, Jaguar Land Rover and Tata. And so there's actually been about 600 vehicles made by Jaguar Land Rover that have had like one of our shoulder devices on a worker, kind of helping to kind of put it together. So it's the same concept. Rather than helping the back, how do we help a person not get a shoulder injury if they're working overhead all the time? But we kind of, it's exciting to think that there's the cars out there or vehicles out there in the real world, and that we kind of like help workers who are kind of like and putting them together. And so, just going to shift gears again. And what I've presented so far is kind of our soft exosuit technology. And for that technology, it's really about motors pulling on cables or ribbons to try and kind of apply forces kind of like to a person's body. And that's really what we've been doing for kind of the lower extremity work and also work that we've been doing on the back, like I just showed there. But for the upper extremity, when we're trying to help people with arm motion, we've been kind of using a different type of technology, and it's using basically kind of air to kind of like power these devices. So we try and kind of integrate pockets inside textile garments, whether it's a glove or a vest or something else, that when you pressurize that, it kind of adds kind of support and force and can kind of help unload people. So, when we were working in this area, initially kind of like not many people had been applying this concept to kind of wearable robots. And some other faculty at Harvard, George Whitesides, Rob Wood, and others were kind of like working in this kind of emerging field of soft robots. So how do you make robots soft? And then we've been kind of thinking about like, well, how do you integrate these components into wearable devices and enable people to actually kind of get benefit from that as well? So I thought I'd show this again, just as like a timeline for like, these projects don't happen in like, 1 week, 1 month, 1 year. It's like usually like a multi-year project of like many, many people kind of like working on it over some period of time. And usually we're kind of creating different iterations of prototypes and then learning from those prototypes. And so this is like really cool because it's like so simple. So if you want to kind of help a person kind of like move, you want to kind of basically kind of program one of these soft actuators to move in the way that the limb or the joint would move. So here we basically have some textile materials, this balloon that can get inflated that goes inside these pockets. And here we have two balloons inside two pockets in this piece of textile. And so when it's off, you can just fold it like a regular piece of clothing. It just kind of looks like a piece of fabric. But then when you inflate those balloons, you can get it to take different shapes. So if I inflate one balloon, I can kind of get it to kind of, I think it's stiffening first. And then if I inflate the other balloon, it can kind of curve and articulate kind of like a finger. So we developed this so that we could integrate it into a glove and think about what are all the different types of motions that, the fingers and the thumb might need to take. And the thumb basically needs some twisting moment as well. And so here you can kind of just see a first prototype. And we might be able to stop the video if it's not kind of the audio is not coming through super clearly. But here's kind of like the first prototype that we made. This is a lady who had muscular dystrophy. And we basically kind of like, put an initial prototype, some of these soft actuators on her hand, actually visited her in her home, brought two pumps, kind of pumped them up. And her reaction was just like, oh my God, for the first time, I'm bringing my two fingers together and I can pinch something. And she actually said that she was beginning, it says it in the video, to not feel human because she, can no longer kind of like pinch. But it's kind of almost funny to think about like a robot might make her more human. So that definitely inspired us to kind of like do more in this area. And so here you can kind of just see a video of the glove. So there's no person's hand inside here. You have to believe me for that. But these are the actuators that would get integrated into the glove. And then there will be sensors that would monitor kind of like what a person is doing. And then you can kind of have this kind of almost have a very natural and realistic movement that can kind of then actively help a person who has hand weakness either open or kind of close their hand. And so you can see that there's really no hand inside here. And so this is kind of one of our volunteers, Charlie, who kind of came in a good number of years ago. You can see he has hand weakness. So kind of doesn't have enough, he has some hand movement, but just not enough strength to be able to kind of grasp kind of that object. But then using the glove is able to kind of help have just enough strength. So it's really about helping people leverage their residual capacity by giving them a little bit more, giving them a boost to be able to do something that they otherwise wouldn't be able to do. And, for people, this can kind of really allow them to be independent in ways that they wouldn't otherwise be able to do. And so after kind of like the initial work and research that we did on that, we really got excited about like, how would we help people actually recover hand function if they had, impaired hand function, say after a stroke. And so we had an effort trying to think about how do we kind of build these devices. We have sensors in these devices that can monitor how people are moving their hands and really kind of create an integrated system that will allow a person to get hand rehabilitation kind of like in the home. So when you think about kind of rehabilitation today, oftentimes the person is having to, get dressed, get in their car, kind of like, maybe get on the T, kind of like go to the clinic, see an occupational therapist, maybe for 45 minutes, maybe spend 15 minutes kind of practicing kind of like moving their hand. And then they're basically sent home and, to practice things on their own, but they don't really have the capacity or the ability to do that. And so it's well accepted that, with rehabilitation, you really just need more dose. More dose is better. You get better if you practice more. It's just hard to practice if you have one of these conditions. And so we started working with stroke survivors, having them come into the lab. We would build simple prototypes out of cardboard, kind of mock-ups of what an interface would look like, show that to them, get their feedback. And then we also kind of built prototypes and we put them in people's homes. And we started to say, here, if you had a robot to help you with your rehabilitation of your hand at home, how would you use that? And so we kind of learned a lot from that. And we ran a study kind of like testing how people would use these devices at home. I'll just show a short video that kind of gives an overview. And so this actually technology got licensed by another startup from our lab, Imago Rehab, that's now kind of working on kind of commercializing and bringing this kind of technology to market. So the idea is that instead of a therapist moving a person's hand, a device can now kind of like move a person's hand. And we created these are not very sophisticated games. And people can design a lot better games than us. But some type of game that would encourage a person to try and do certain tasks. And then we would detect that a person is trying to do those tasks and then have the robot only help after they were trying. We didn't want the robot to do all the work. We really wanted people to engage with the system. And then the nice thing is these devices can collect data and the therapist can remotely look at that data and engage with the person and see how they're doing. And kind of, we don't think these devices are going to eliminate, the physical therapist or the occupational therapist. But the idea is that they give them new tools to allow people to do this at home, where they can do it like much more, but still have the therapist be kind of like a meaningful part of that experience for people. And so here's just kind of like one case study. I won't get into kind of lots of data, but this is a person, who at the start, of working with us, this was in the lab a number of years ago, had, kind of like very, very contracted hand, kind of very, very stiff hand. And then kind of like after kind of, a period of time participating in our study, really kind of like had great improvement in terms of being kind of able to open their hand. And then that means that people are now able to be more functional and kind of do activities that they wouldn't normally kind of be able to do as well. So I've talked a lot about robots so far that help you when you wear them, but we're equally as excited about robots that allow people to practice better movement and with much higher dose than would be common in current rehabilitation settings, to then be able to kind of hopefully not need the device in the future as well. So in terms of kind of like going up the arm, I'll talk a little bit about our shoulder work. So we're also trying to think about people who have arm weakness. How do we help them? So here you can kind of see a device that's kind of like inflating. So this is a mannequin with a balloon basically integrated into a shirt. And so, this is just one example, kind of just to show a quick video of a person who would have a hard time. This individual has ALS, and would have a hard time being able to kind of like perform this task because they don't have enough strength and control over their arm, but they have some. But the robot, it's a little bit hard to see. But once that's engaged now, the person is able to leverage that residual capacity and perform that task in a way that they wouldn't have been able to kind of on their own as well. So it comes back again to that, rigid exoskeletons may be great for people who really need large amounts of assistance. But for people who have some capacity, but just not enough, we think soft wearable robots, can kind of play a big role there. This is also John, who kind of spent a lot of time working with our team and was really, really helpful to us. He also had ALS. He came in, he participated in our study, and we were inspired by him. And he said, I really want to take one of these devices home, and I want to try and use it at home. So we actually built a version of it that wasn't as smart as our smartest devices, because we weren't really ready for that with this device. But we kind of had a simple button and interface that he could press, and we can maybe play that video again, that he can press, that allows the device to trigger after a certain number of seconds, and he could kind of time his movement to that. And then he was able to use this to eat independently at home for 3 months, when he wouldn't otherwise have kind of been able to do. And so working with John and his partner and people like him really kind of helps kind of us understand kind of like the real needs of people. And I think a big part of it is helping the individual, but a big part is also helping the caregiver. Like, there's a lot of people who are at home kind of like, being the primary carer, for kind of like a person who has ALS or who's suffered a stroke, and there's a fair amount of burden on them too. So, if we can help the individual be more independent, I think it has a knock-on benefit of also meaning kind of that those who are caring for that person maybe are able to focus on other things or more engaging things, rather than just having to kind of, do certain tasks that maybe we can help with these robots. So you can imagine kind of combining these devices together. So we're also kind of like excited to think about that here. You can kind of see a person kind of like wearing the shoulder device and the glove device together. And so I think we're a little bit away from that. We're not kind of there yet on that, but I think that's really our vision, is to try and think about how do we restore upper extremity function through kind of these inflatable soft robots that could all be powered from a very kind of small compact compressor that a person would wear, and then selectively inflate these different balloons, depending on where people need help for specific tasks. So the last project I'm going to talk about is just 2 slides. I'm glad I included it, given you mentioned the YMCA and strength training. So we have another startup that kind of spun out of our group that is called Work. So you can kind of check it out. But the idea there is like, how do you quantify strength training? We all wear Garmin and Apple watches or Whoop that kind of like monitor kind of like our movement or our cardiovascular kind of like metrics. But really, when you think about strength training, it's hard to quantify an exercise because like there's so many different exercises that you do. So kind of the team in the lab, before they spun out, had developed some pretty cool machine learning and AI algorithms that could automatically recognize what specific motion a person is doing. And then for each of those exercises have a specific metric that would kind of like really quantify kind of how well kind of like they're doing that movement. So you can, imagine kind of like at the moment, the kind of use case is CrossFit. So they're kind of very much focused on CrossFit. And here's kind of just a video that kind of gives the idea. You would have to put on 2 sensors. So I think it's hard to do with just one sensor kind of like on the watch. But the idea is that it would automatically know what specific exercise you're doing, whether it's a push-up or a squat or a bicep curl. and then it would be able to kind of like track those over time, and give you kind of feedback on like whether you're doing it well. So I think there's other approaches for this too. You can use cameras and vision and other things. But I think the challenge here that the team is trying to solve is like, how do you do this with a wearable? Like, what's a wearable that you could use to kind of quantify your strength training activities? So if you want to check it out, it's kind of pretty cool. And they were based in Allston, kind of like for a while in the iLab, and kind of before kind of moving out of Allston and Cambridge. So I'm just going to kind of wrap up with a few slides. And one is like, I think we have a growing community that are excited about this area, and of kind of like devices and technologies to assist human health and to assist human performance across many different aspects. And we launched the Harvard Move Lab kind of about 5 years ago with support and a grant kind of like from Mass Tech. So really kind of grateful for that. And we really look at this as a hub for kind of bringing together folks from across the different schools at Harvard. There's a lot of expertise across the business school, School of Public Health, School of Engineering, the medical school, but a lot of the hospitals in the Boston area too. We already work with many of these and other institutions like Boston University that can kind of like, if we kind of pool our effort together in this area, I think we can really kind of have Allston and have kind of like Massachusetts be a leader in this area. And so we've been working towards that and trying to think about like how we kind of grow our efforts in this area. And then the Move Lab specifically, we have a space that's dedicated to this new initiative, kind of like in the new building. And this is kind of like what the grant from the Massachusetts Technology Collaborative kind of like helped us kind of like spin out. And so, we have a dedicated space, and this is not just a space for kind of academic research. This is a space for what we call translation. So here we kind of have staff engineers who would be kind of like, have experience working in industry. JP is one of them who's here. You can put up your hand, JP. But people who have worked in industry, people who have developed software, who have developed embedded electronics, who have kind of done apparel design, but really kind of like bring more of a product development and kind of technical development mindset. So after we show something is promising with a research paper, how do we kind of like take it further along? Like I've been saying, I was a grad student once. Grad students are good at making things that work. Once you get data, you graduate, and it never works again. That's like very, very common. So, I think if we want to make things with a higher technology readiness level, we need additional expertise. And that's where I think we're trying to kind of like use the Move Lab as a way to bring those technical staff together, have those technical staff be mentored, and have them work closely with the academic teams because they can't do it on their own. We have all this great research and knowledge that's happening in the university setting, but how do we partner that with kind of more kind of product development kind of expertise as well? So we have a dedicated space. We have a person, Paul Sabin, who's kind of overseeing kind of the space. And we really look at it as kind of bringing together the right people, the right teams across institutions and disciplines to kind of like really move these projects forward. And like I was saying for kind of one of the earlier projects, in this space of like wearables, we really want to be able to kind of build devices we can give to people and test in the real world. Because if we give devices to people and they don't use them, then we know we still have work to do. And so until we can build devices that people don't want to give back to us, that's when we know we'll have really kind of like made progress kind of like on a lot of these projects. And so this is kind of just summarizing kind of like what I just said. We really see this kind of gap between academic research and kind of getting things out to the real world. So we think the Move Lab can kind of provide these kind of pillars or stepping stones in partnership with other groups kind of like across Harvard to kind of really kind of get from this kind of like through this kind of like challenging kind of like cliff that we need to climb. So this is our vision, kind of like this is really kind of like what we see in the future is there's wearable devices, that we talked about for monitoring kind of like ourselves. But I think there's kind of capacity to do even more kind of in that area. But then I think there's going to be the next layer of wearables that really kind of help people with movement and help people with rehabilitation kind of like in the home, in the community, or help people not get injured as well. So this is kind of like really where we hope we see in the future. And then kind of the Move Lab and kind of all of this is really about educating people. So like that's our primary goal as a university is like we're training kind of the next generation of innovators and leaders in this space. So we're kind of trying to make sure we kind of like are, creating good opportunities for people to learn engineering skills, data science skills, et cetera. We're really about kind of convening and bringing together kind of all the relevant stakeholders. And then ultimately we want to translate things kind of from the lab out to the real world and have impact from the research that we do. And so kind of in terms of kind of impact, I think there's a couple of things that I just want to highlight. Like one is the Bionic 5K. So this is a really fantastic race that who's here, Will Borden, launched and has been running kind of like for a good number of years now. That is kind of in Cambridge on May 17th. It's a 5K. I think there's also a mile kind of like as part of it as well. But a really amazing day that kind of brings together technology and individuals kind of with disability to try and kind of like rethink kind of like what does kind of human performance really even mean, and it means different things for different people. But it's an amazingly inclusive event, and it's inspiring to kind of see all the different people who participate and join. Dan Nosson, is a former Navy SEAL. He has kind of 2 graduate degrees from Harvard. Will was telling me, and this is a picture of him here. But he's currently kind of in the Paralympics, kind of like, representing kind of the United States as well. So it's just been amazing seeing Will grow this race. It's now probably over 1,000 people that would be kind of like, participating in it. And it started at kind of like a much smaller scale. So it's really grown over the number of years. And then we also hope to have this in Allston, kind of in the future as well. So I think that's something that we want to work on, but encourage people. Will be here. He's wearing a hat that says Bionic 5K or Bionic Project on it. And you could talk to him at the reception if you want to learn more about this. And then the other plug that I just want to give is our lab has a rock band, as every good engineering research lab has. And so the name of the band is called Luigi's Fish Tank. I don't fully understand like why the name is the name. But basically kind of the team basically kind of submitted an application in collaboration with our group to kind of have an event that brings together music, technology, and disability kind of at the Hat Shell. So that's going to be on June 3rd, kind of in the evening. We just got accepted kind of like a week ago. So this is, we haven't really done any concrete planning. But we're kind of starting to plan for that as well. But I would just keep an eye out for kind of that. There's going to be some announcements that go out about that. But it's kind of hopefully a really exciting to kind of bring bands and kind of performers, from across kind of like, the community here in Boston. And then we hope to be able to showcase some technology that is improving people's lives, as part of the event, and maybe have some demos in there that people could kind of observe or maybe even kind of take part in as well. So I think I'll kind of end there, with kind of like one more slide, sorry. I do want to give a shout out to kind of an educational work, because we've been doing it with the Harvard Ed portal over a number of years, but we put a lot of the information for our core soft robotics work online. So if you go to softroboticstoolkit.com, and you can actually kind of, see a bunch of cool soft robots. You can see videos on how to make soft robots. There's some materials for educators and for students to kind of get involved in. We've had competitions, we've run workshops, but it's definitely been a topic in a field that has kind of inspired young people to say, oh, I can build a robot really quickly, and it doesn't have to be the traditional type of robot that everyone kind of thinks about. We don't have to have robots that just fight in cages, basically, but we can build them for lots of different applications. And so that's kind of a resource, and in the future, we may have some more programming on that kind of as well. But I'll just stop by saying, like, this is really kind of like a team effort. There's kind of lots of people who have contributed to this over kind of like really many years, lots of sponsors, who have supported our work, and kind of enabled all this to happen. And happy to kind of talk to people more outside. And if there's time for questions, I'm happy to kind of also take questions here now today. But thanks for listening.
Yeah. All right. Anybody would like to kick it off?
Hey, first of all, congratulations. The work that you're doing is amazing. I have had friends and family members who have passed from ALS, and my best friend is currently experiencing Parkinson's at a young age. So the work that you're doing is incredible, and I can't thank you enough for it. Just a generic question. I was curious to know if you could speak a little bit about how AI is both complementing and accelerating your research, and perhaps bringing some of these products to market.
Yeah, that's a great question. So with all the devices that we have, there's a lot of data that we're collecting. And sometimes it's like so much data, kind of it's overwhelming. So I think AI is definitely a tool that we're using more and more to make sense of that data that we're collecting with these devices. I didn't get into some details, but we do have kind of algorithms that you could call machine learning or AI that are sometimes learning how people are walking with these devices, and then personalizing and customizing the assistance to them for their specific need. Because we all move and we all walk a little bit differently. And if you have kind of an impairment, there's even greater diversity in kind of movement patterns. So one thing we've learned is like, the same controller and the same settings won't work for each person. So I think that's really where AI can have a big role, is kind of personalizing how these devices are best helping people. Yeah.
Most of the people you showed were male, and they were reasonably medium build. And I'm wondering what happens to for women, whether the weight becomes a problem, because your average woman is not that big and not that heavy.
Yeah, that's a great question, and thanks for pointing that out. I would say we strive in all our studies to try and have, kind of like as equal as we can mix kind of like of gender. Maybe some of the videos I showed, I should have maybe a bit more diversity kind of like in the people that we've worked with. But I'd say for all studies, like whether it's people with ALS or people with stroke or kind of like people with Parkinson's, we do have kind of people from both participating. And I'd say it's probably like you're saying, a little bit less about kind of like there are gender specific differences in terms of fit and sizing, and we do work on those and we try and make devices work for kind of both groups. But I think that it's really about the size of a person. So we're gradually kind of like coming to the conclusion that the one ankle exoskeleton design may not be for all, and you may need to have kind of like a small size and kind of like a large size. And so the larger you make it, the heavier it gets, but the more power you can provide, and maybe you need that for a bigger person. But if it's a smaller person, maybe they don't need that full power, so they're just wearing a heavy device when they wouldn't need to wear the heavy device if we could have a smaller motor and a smaller battery for them. So I do think the future is going to be kind of like different sizes of devices like this that would have different capability, not only just for gender, but largely for body size. I think that's going to definitely be a big important factor. Yeah. Thanks for the question.
Hi. So my question is, are you guys tapping into, I didn't see evidence of it, but are you able to tap into or looking to tap into sort of like central nervous system drive, motivational things to gather that the desired motion of what someone wants rather than physically responding to emotion, which is already kind of occurring at some level?
Yeah, that's a good question too. So we have a collaboration with folks at Brown and MGH, which is led by Lee Hochberg, who's a faculty member at both institutions. And so they're developing what they call BrainGate. So basically kind of like an implantable sensor that would kind of go inside a person's skull and be able to kind of sense kind of intent by looking directly at the brain signals. So obviously there's other companies doing that kind of like now in that space, but they've been doing it for a long time and have really got good at developing kind of like the science of like, how do we interpret those signals and actually tell what a person is trying to do? So we started a collaboration with them probably like 4 or 5 years ago, where we first gave them our glove, and they were able to show that a person was able to kind of using their thoughts, kind of like open and close their hand, kind of like wearing the glove. And more recently, we've given them our shoulder device, and they're able to kind of like now show that a person can kind of like move their arm and think about that. And that's kind of why I showed the video of combining these systems together. Like our vision for them and what we want to do with Lee and his team in the future is really have kind of like a full arm sleeve that they would be able to then take those neural signals and be able to restore motion for a person who doesn't have any volitional movement at all. I think it is a harder problem, but it's definitely something that we're kind of interested in and taking kind of baby steps on to work towards. Yeah.
Hello. Oh, first of all, thank you so much for your presentation. It was really inspiring for me as a student in this area. So if you can talk a little bit more about the choice of using pneumatic actuators in the upper limb regarding the technology for the lower limb that you used I believe it was cable driven actuators, right?
Yeah, it's a great question. And I think in summary, I think when it comes to the upper limb, I think pushing is easier than pulling. So if you wanted to have cables come down from, like, say here, the back or the shoulder down to the arm, making that comfortable and being able to apply enough force into those cables, I think would be hard. So we believe that pushing the arm up is better than pulling the arm up. So that's kind of like probably the biggest reason. And then for walking and back movements, I think they're much faster and much more dynamic. And so a system needs to be much more responsive, which a pneumatic air-based system is not as responsive at. But for the upper extremity, I think if a person really has no movement, if the movement is slow, that's maybe still acceptable if you're restoring that function for them. So I think that's kind of the trade-offs that we were thinking through in that. Yeah. Yeah.
Hi, I was wondering about the relatability because I do research on the service education for holistic health. So we were working on like diabetes, like type 2 diabetes or other kind of body alignment, such as treatment from acupuncture and chiropractor, right? So that's more like the body elements with movements and parts of your existing muscles and body in the body already. So how do you connect that relatability with the AI muscles and your own muscles to adapt with each other, besides the AI adapting to the human body? Because I think in the long term, that holistic adaptability would have to reach at a point that they have to balance each other and be consistent over time.
Yeah.
How do you measure that balance and not having one breaking the other, or out of alignment, or have a surprise?
Yeah, that's a really insightful question. I don't think I have a quick, easy answer for that one, but I would say that what you're getting at is kind of a big challenge for the field. Is like, how do you think about co-adaptation? Like, how does the device adapt to the person, and how does the person adapt to the device? And so Patrick Slade, who's a colleague kind of in the School of Engineering and Applied Science, is definitely interested in that, and we've been kind of thinking about some studies in that area. But it's definitely kind of like there's still a lot to do there. That's a very rich area of research, I would say, but both are equally important. The first time you put on one of these devices, you might not get the most benefit. Your body and your nervous system has to learn how to get that benefit. And the same way that I mentioned, AI can actually help the device get better at learning how to help you. So it's like, how do you help those two processes work together at the same time? I think that's an open research question. It's a good question.
Well, first, thank you for the work that you do. I was beyond impressed when I found it, when I was searching for this. And as you know, my interest is low-income populations in public health. And I was just wondering if there's been conversations about bringing this also to rheumatology. As you know, it's the degeneration of the joints. And I noticed there's a strong focus on the muscle, because that's where the research is at. But has there been any conversations of also bringing that to rheumatology?
Yeah, that's a really good question. And our own group has not worked on that or tried to work at the joint level. But again, Patrick Slade, who I just mentioned, who's a colleague at SEAS, and he's working on a device for knee arthritis or osteoarthritis, which maybe relates to that, where kind of like it's the loading of the joint that kind of like causes a lot of pain for people. So how do you develop devices to help reduce that unloading, which I think there are ways to do that. So I definitely think that there's applications for that. And then the other thing that's kind of like interesting is I do think these devices can have an effect on inflammation in the body. Not the way I presented today, but we've done some work with Dave Mooney, who's in bioengineering. And I think kind of by kind of like compressing muscles and helping strain muscles, I think you can kind of like impact kind of the immune system and inflammation. So I think there's kind of scope for that in the future as well. Yeah.
So we have a great question from the chat. So I'm just going to read that quickly. My grandfather struggles to write because his hand trembles, making it difficult to hold a pen steadily. Since the prototype hand device has already helped someone hold a drink can, could it one day be developed to further assist people with hand tremors in writing as well?
Yeah, that's a great question. Thanks for that. We actually so I teach a medical device class, and we have a group of students at the moment who are working on kind of like a hand assist device that may be kind of like slightly simpler version compared to kind of what I've presented there. And the idea would be able to help people with kind of like two grasps, like one a pinch grasp and one kind of like a power grasp. So I think there's still a lot of scope for that, and we're still interested and motivated to work on that. And I think trying to keep the device as simple as possible would be kind of like our goal. Yeah.
Excellent. Well, I think we're going to end it there. Thank you so much.
Thanks.